So the question about whether volume or temperature, T1, V1, P2, what variable shows on top of the expression, it really depends on the problem. And I'm going to first talk about the combined gas law, which looks like this. Now, this kind of equation is used for problems where P, V, and T change. Okay, so, just to make up some numbers, let's say, let's say P1, 1 atmosphere, V1, 1 liter, and then T1 was 273 Kelvin, let's say. And then in the problem, you also find out that the second pressure is at 2 atmosphere. The volume has decreased to, 0.25 liters. And then T1 is the question mark. So what variable goes on top, what variable goes on the bottom? Well, really, it just depends on the algebra that's required to solve for V2 or T1 here. So what that would look like, well, for an expression like this, if I want to solve for T2 is on the bottom of the expression, right? We need to get to an expression where, it's like, oops, and that should be 2 and 2 there. It should be T2 equals, some expression. So that means that T2 needs to be pulled from the bottom and actually put on the same line as all the other variables. And the classic way of doing this is cross multiply and divide. So cross multiply, if you multiply the bottom T2 times the P1 and V1, you get this expression. Now I'm choosing to put it on the left-hand side. And then the remaining expressions would look like that. So we've removed the fraction look of the problem. We've put all the variables on the same line in the equation. And now the next step, if I want to, finally solve for T2, then what I need to do is now, right, the step was cross multiply and divide. The divide part would come in here, where what I'm trying to do is isolate, I'm trying to isolate T2 all by itself on the line. That means that I need to move these two variables, P1 and V1, to the other side of the expression. I can do that by dividing both sides of the expression by those two variables. On the left-hand side here, P1 and V1 cancel out, and now I have a new expression that I can finally say is my final formula. And then again, the question is, which temperature is on top, which pressure is on bottom? Well, again, it just depends on the problem that's presented to you and the algebra that you have to go through to figure that out. In this particular example, where T1 was what we were solving for, then it placed T1, P2, V2 on top, and then P1, V1 on the bottom. And then just to finish this particular problem off, let me just go ahead and plug and chug these values here into the expression and see what I get. Now, in any type of calculation that you do for Chapter 11, whether it is the combined gas law or Charles's law or the ideal gas equation, temperature always needs to be in Kelvin. Now this expression, or this problem I made up, I just chose kelvins to make it convenient. And then the other units, so for the combined gas law, as long as the pressures are the same and the volumes are the same so that they can cancel out in the problem, you're fine. In the ideal gas equation, since R has the units of liter, atmosphere, mole, and Kelvin, then that means that temperature needs to be in Kelvin. N is, of course, moles. The volume needs to be liters, and then pressure needs to be in atmosphere. Getting back to the combined gas law here, the problem that we're working on, right, that guy. As long as the units cancel out here, that's really all you're looking for. And the answer I'm coming up with is 136.5 Kelvin for this problem. I'm kind of ignoring the sig figs here. I mean, if I was to factor in sig figs, well, really, I could only keep one sig fig because the one and the one down here that I made up has one sig fig. I'm not going to do that because it's going to ruin the number. The other thing I just want to point out is that this is in Kelvin, and oftentimes they want the value in Celsius. So make sure to read the problem, and if it's talking about temperature, make sure that you give it in Kelvin or Celsius, again, depending on what it's asking for. The formula that you always see is Kelvin is equal to Celsius plus 273. Well, if we solve for Celsius, that would be Kelvin minus 273. So in this particular problem, if it was asking for Celsius value, you would get a negative number. Well, actually, I just happened to split it right in half just by coincidence, just by chance. It's 136.5 degrees Celsius. Again, that's only because of the math in the original values up here that I chose on the problem, okay? I hope that was helpful, and let me know if you have any questions. Okay, thanks.